How's it going, guys? Today in this video, we're going over module 1.3, day 1. And we're going to start with this from the decimals activity, which is part of your homework from the previous night. I'm just starting with this because this is very important, and if you didn't do it, you should have this written down. That's on page 30 in your notes. So your A value is a reflection of the x-axis. It is a vertical stretch or compression. Your B value, that's both a reflection of the y-axis and a horizontal stretch compression. It tells you one of those two or both. Our H is a horizontal translation, which is a fancy way of saying you're shifting left to right. And your vertical, your K is your vertical translations, which is just a fancy way of saying you're shifting up or down. All right, so you need to copy this down, pause the video, and copy it all down. We're going to keep going. This slide right here is just telling us about parameters, what they are. And that's what we saw in the previous slide over here. That A, B, H, and K are what we call parameters. Those are the parameters we're going to be dealing with in this course. And what they do, or what a parameter is just the numbers or the variables that actually transform the function. So you have a function that transforms into a different function. That A, B, H, and K, or what's transforming the function to a new one, is what we call our parameters. So if we keep going here, we have a graph g of x equals f of x plus k, where k is the parameter. We're going to let k equal 4, so g of x will equal f of x plus 4. So we're going to figure out this table down below in the bottom left. We're going to fill that all out, and we're going to see how we actually transform from our original equation of f of x to our transformed equation of g of x. So remember, f of x is just a fancy way of saying y for the most part. So g of x equals f of x plus k will be pretty much the same thing as g of x equals y plus k. So the transformation rule, you have our original point xy, and we transform the original point to our new one by x comma y plus k. Or in other words, we're just going to add 4 to our original y value to get our new transform point to figure out our new transform graph. So for instance, on point A, we have this point negative 6, 1. We're going to put that into our transformation rule of x comma y plus 4. And when we do, we plug in our x and our y term into that transformation rule. We get the point negative 6, 5 because we just add 4 to our y value of 1. So with B, if we do the same thing, we get negative 3, comma 2. Negative 2 plus 4 is 2. Then we get 1, 6, 2, 4, and 5, 10. We're adding 10 to the y because that's our transformation rule. All right. So once we do that, we're going to go back and plot these new points. So our first one is negative 6, 5. We'll be over here. Negative 3, positive 2. 1, 6, 2, 4, and 5, 10, which would be somewhere up there. We're going to connect the dots. Oops. Up to there. There we go. And we can see that this red line is pretty much the same thing as that black line. All we did is we took the original line, the original graph, sorry, not line, but the original graph of f of x, which is the black one. We took it and we moved it up 4 units. And that's exactly what we said K was in the first slide of the lesson. K is a vertical translation up and down. So when K is positive, we're moving the graph up 4. All right? So when K is positive, the graph moves up. And I want to go back to this transformation rule. So we really only gave you part of the transformation rule right there. The full transformation rule, which we're not really going to use in today's lesson, but I want you guys to see it and get familiar with it, is this bx plus h, ay plus k. So remember, b, h, a, and k, those are all our parameters that we're going to be using in this course to transform a function, f of x, to our new function, g of x. And that'll be the new that'll be our full transformation rule. Just write it down, have it memorized. We're going to be using it all year. So it's a good time to start looking at it and memorizing it and getting used to it because we are going to be using it very often this year, and I just wanted to, introduce it to you guys. So we're going to keep going. All right, on B, we're told we're going to do the same thing now as before, but we're going to have a negative k value. So we have g of x equals f of x plus k, but in this case, our k is -3. So in this case, we have g of x, that equals f of x minus 3. Remember we said f of x is kind of like a fancy way of saying y, so y minus 3. And that's exactly what our transformation rule is, x comma y minus 3. And you could have used the transformation rule I showed you in the previous slide. Either way, you get the same thing, x comma y minus 3. Or in other words, our k is our vertical translations up and down. We take our graph and we move it down 3 units. Or in other words, -3 from our y term. So when we do that, this is what we should get on the screen. Five, 3. That's what you should get. And again, we're gonna graph it to see exactly what it looks like. So -6, -2, -3, -5. That's -6. There we go. 1, 2, 3, going down 3, and finally 5, 3. That's what we get. So we're getting this count again, but that's what we got. And again, that graph of g of x, that's what the green one's called, g of x. Well, our original graph f of x is going to be the black one. Our transformed function g of x is our original graph translated down to the units because our k is -1. Your k is negative, you're moving down by k units. In this case, k was -3. We moved down by 3 units. We took the f of x, the original black graph, and moved it down 3 to the green one. All right, now for C, now graph g of x equals f of x minus h, where h is the parameter. So h is 2, and we get g of x equals f of x minus 2, and we're going to complete the table like before and graph our new function. So when it comes to h's and b's, or really anything that's inside of this parentheses and of f, it's going to act kind of weird. It's going to act differently than you expect. All right, it's going to act almost like the opposite of what you'd expect. So for C, we're told h is 2, but our equation is f of x minus 2. That equation, f of x minus 2, really means that h equals +2. Because remember the original equation, if you go back to page 30 in your notes, that g of x equals 1 over b, f of, a times f of x, f of 1 over b, x minus h. You have that x minus h inside the middle of it. So our h term is going to be x minus our h term. So x minus a +2 is the same thing as x minus 2. X minus a -2 gives us x plus 2. So you have f of x plus 2, for instance. Instead, f of x plus 2, that gives us an h value of -2. One way to think about it is that your h term is going to be the opposite of what you expect it to be. All right, you see f of x minus 2, you think it'll be -2, but it's really going to be a +2. All right. So I just want to touch on that really quickly. So we're going to keep going now. Our h is 2, and our h, remember that's our horizontal translations, left and right. That's directly affecting the x inside the parentheses. You have an x value, and we're minusing h from it, or really we're adding h to it. So that means our h is 2. We're going to take our x values, and we're adding them by 2. All right? So a is now -4. Our new a anyway is -4, 1. Our new b is -1, -2. Our new c is 3, 2. 4, 0. And 7, 6. We add 2 to the x value. So if we go ahead and plot it, we have -4, 1. -1, -2, 3, 2, 4, 0, 7, 6 will be right about here. That's what we get. And that's what our transformation is going to be. So we see that we added 2 to the x value, so our translation is translation 2 to the right. So we look at our parameters to figure out what we're doing to our graph. Our h is 2. That means we're shifting to the right by 2. All right? So that's what it is. Our h is 2. We have a horizontal translation to the right or a shift to the right by that 2 value. Going down here, in general, how is the graph g of x equals x minus h related to the graph of f of x, and h is a positive number. Or in other words, if you have g of x equals f times x, let's say minus 7, some positive number, where h is a positive number. That means our h is 7, a positive 7, and we're shifting to the right by 7. So you have f of x minus 7, or x of any positive number minus any positive number. You're shifting to the right by that positive number, by that h value. So like I said, it's going to be kind of the opposite, but that's what's going to happen with h. All right, so D, make a conjecture. How would you expect the graph of g of x equals f of x minus h to be related to the graph of f of x when h is a negative number? Or in other words, let's say g of x equals f of x plus 3, for instance. That's telling me my h is negative 3. Since x minus negative 3 is x plus 3, our h term is negative 3. And that means we're shifting to the left by 3. It's a horizontal translation to the left by 3. So that's what happens when h is negative. You just go to the left by 3 since you're minusing x by the h term now. All right. Now, reflect. Suppose a function f of x is a domain of x1, x2, and a range of y1, y2. When the graph of f of x is translated vertically k units, where k is either positive or negative, how do the domain and range change? So all it's saying is that let's say you have some graph and you move it up or down. All it's doing when you're moving it up and down is you're just messing with the y terms, right? You're just moving it. You're changing the y value. Sorry, you're moving the graph up or down. So you're moving the y values by a k value. So the domain doesn't change. The domain does not change, but the range will now be y1 plus k, comma y2 plus k. And obviously it's going to depend on if k is positive or negative, if that makes it bigger or smaller. But that's what happens. You add k to the range, and that's what your new range is going to be. And 2, suppose a function f of x is a domain of x1, x2, and a range of y1, y2. When the graph of f of x is translated horizontally h units, where h is either positive or negative, how do the domain and range change? So in this case, when we have a graph and we're just taking it and moving it left and right, we're not changing the y. The y stay the same, right? It's going to be the same thing. We're just moving it left and right. The only thing that's changing is our x terms, right? So if our x terms are changing, that means that's what we changed in the domain and range. Only the domain changes to be x1 plus h and x2 plus h. Depending on whether h is positive or negative, that's what it's going to be. All right. So let's keep going. Now we're going to talk about stretches and compressions of functions and function graphs. So we talked about our h and k terms, where we have translations left, right, up, and down. Now we're going to talk about our a and b terms, where we stretch or compress and even reflect the graphs. All right. So it sounds a little confusing, but we're going to break it down part by part. So on A, we're told the first graph g of x equals a times f of x, where a is the parameter. So let's say a equals 2. So we have the equation g of x equals 2 times f of x, or in other words, g of x equals 2y, right? Y is kind of like a fancy way of saying f of x. So we're multiplying the y's by 2. So our transformation rule is x comma 2y. And that means we're just going to be multiplying each y value by 2. So just go ahead and multiply each y value by 2. So that b becomes negative 3, negative 4. Then 1, 4. So d stays 2, 0, and that's perfectly fine. 0 times 2 is still 0, so that just doesn't get stretched. It's perfectly okay. All right, so we have our new points. We're going to go ahead and plot them. We have negative 6, positive 2, negative 3, negative 4, 1, 4, 2, 0 stays 2, 0, and 5, 10 will be up there somewhere. So just connect the dots. And what we can see when we connect to the dots is that we took the graph, we took the graph and we just stretched it, right? It's much longer now. It's a stretched out graph. That's what happened. All right, so, and that's what happens anytime A is greater than 1. All right. So when A is greater than 1, you're multiplying a y term. So that y term is going to get further away from the x-axis, or a simple way to say it is just that you multiply any number by a term that's greater than 1, so like 2, 3, 4, 5, 6, whatever, it's going to get bigger. All right, it's going to get bigger, and that number is going to get bigger, it's going to get further away from the x-axis, or in other words, it's stretching out. All right, so just keep going. Let's see what happens when A is 1/2. So when A is 1/2, we have g of x equals 1/2 of f of x, or in other words, g of x equals 1/2 y, right? F of x is kind of like this, y is like saying the same thing as f of x, so we're going to use them a little interchangeably. And so we're just multiplying our y terms by 1/2. So x 1/2 y. We're going to multiply all our y terms by 1/2. So let's go ahead and do that really quickly. You should be getting what I get on the screen. 2, 0 stays 2, 0. That's perfectly fine. E becomes 5, 3. So that's what our points are, and we're going to go ahead and plot them like we always do, so you can see exactly what's happening. I'm not sure why I put x instead of 6 or -6 here. That should be a -6. So -6, comma 1/2. There we go. So we'll go ahead and plot these. -6, positive 1/2, -3, 1, or -3, -1, sorry. 1, 1, 2, 0 stays the same, and 5, 3. So we can see, once we connect these dots, that when A is a negative number, no, sorry, not negative, but when A is a number between 0 and 1, that we're compressing, right? It's kind of like the same thing as before. You have an A term between 0 and 1, like 1/3, 2/3, 3/4, whatever it is. A number less than 1 greater than 0, you multiply that with a number, you're going to get closer to the x term or closer to 0, or you're getting smaller, right? So that's just what's going to happen, and that's what's happening here. So that's why it's a shrink when A is between 0 and 1. So we're going to keep going. Now we're going to graph g of x equals f of 1 over b times x, where b is the parameter. And we're going to let b equal 2. So that g of x equals f of 1 over 2x. So like I said earlier in the video, when it comes to f of x, especially the b's and the x's, everything inside the parentheses is always going to act different than you expect. It's going to be a little weird. So here, we have a b value of 2. And that gives us the equation 1/2 x, f of 1/2 x. All right, remember the equation, it gives us f of 1 over bx. All right, go back and look at the general equation on page 30 of your notes. We have a 1 over bx. Our b is always going to be flipped. So to figure out your b term from the equation, you have to look at it, and you have to flip it. All right, because it's in the form 1 over b, so you have to flip it. So if f of 1/2 x, you flip that 1/2, you flip the term you're multiplying x with to give you 2. It's one of those weird things you kind of just have to memorize. It is accept it for what it is. You know, it is what it is. Take that term you're multiplying x with, flip it, that gives you your b term. All right. So our b, we say, is 2. So that means we're going to multiply our x by 2. And we're just going to multiply all x's by 2. All right, so there's not much else to say. Just go ahead and multiply all those terms by 2. And you should get what I get on the screen right here. And once you do that, we're going to go ahead and plot it like we always do to see exactly what it looks like when we have a b value of 2. So we have -12, 1. That's going to be way out here somewhere. Let's say right about there. -6, -2, 2, 2, 4, 0, and 10, 6 will be out here somewhere. So connect the dots. Didn't connect it very well. All right, good enough. Anyway, the point is just to see that when you have a b value of 2, or you have a b value greater than 1, that you're taking the graph and you're stretching it horizontally. You're taking further away from y, or further away from 0, because when you multiply any number by a number greater than 1, it's like 2, 3, 4, 5, like I said before, you get further away from 0. All right, so that's what's happening. You're stretching out the graph. So in general, how is the graph of g of x equals f of 1 over bx related to the graph of f of x when b is greater than 1? So let's say we have some g of x, and that's equal, let's say f of 1 over 7x, whatever you want it to be, as long as the b in the bottom of that fraction is greater than 1. What happens is we're going to have a horizontal stretch, right? We just saw that. But what you could do is always try to figure out what your parameter is first. So we can see here that our parameter here is b, and that's going to equal 7. You take the number you're multiplying the x variable with, and you flip it. 1 over 7, when you flip it over, you get 7. When b is 7, that means you're having a horizontal stretch. So I'll put h stretch for short. All right, you take the function and you stretch it by a factor of 7, so it's a horizontal stretch. We'll keep going. So now on 4, we're going to reflect. Suppose the function f of x has a domain x of x1, x2 in a range of y1, y2. When the graph of f of x is stretched or compressed vertically by a factor of a, how do the domain and range change? So this is when we're stretching by a factor of a only. So actually pause the video for a bit, see if you can get yourself, think about it for a little bit, what you think is going to happen to the range when you multiply the graph by a. You multiply f of x by a. All right, so we're back. So what's going to happen is the domain doesn't change, right? If you're stretching it up and down, you're not moving the x's. The x's stay the same. You're just stretching it up and down. All right, so the range is actually going to become 2y1, sorry, 2, we didn't say it was 2, it's just a. It's going to be a, y1, a, y2. And really, if you go back here where we had an a, it's greater than 1. We saw on our graph right here, give you a graph, our domains didn't change. All we did was we stretched each point by a factor of 2. The range got bigger by a factor of 2. So multiply the endpoint and I don't say endpoints. But yeah, you would multiply the endpoints of the y1, y2 by your a factor. So that's exactly what you do. That's what we said here. The domain does not change, but you multiply the y1 and the y2, the endpoints of your range, by a, by the factor that you're increasing by, you're stretching by. All right, for 5. We already kind of talked about this, so I'm just going to show it to you while I talk a bit. I didn't copy the rest of this to translate it h units horizontally and k units vertically. I didn't see a point. But really, when a is greater than 1, you have a you have a vertical stretch, and when a is between 0 and 1, you have a vertical compression. And it's also saying that you can have multiple parameters and multiple transformations all in one. And we'll see more of that in the next video, in the next units. But for now, we're just focusing on one parameter at a time. So, but for here, when your a is between 0 and 1, we have a vertical compression. And same thing with this bottom one here. It's saying the same thing. If your b value is between 0 and 1, you have a horizontal compression. When your b is greater than 1, you have a horizontal stretch. And same thing, you can have multiple parameters in one. You have your b, h, and k all together, and you just have multiple transformations happening all at once. And that's perfectly okay. And that's where we deal more with that transformation rule I showed you guys at the beginning of the video. But we'll be using that more in the coming lessons. All right. So now we get to probably the more confusing part of the lesson, is where we talk about even and odd functions. So this first link right here is supposed to be even. So an even function is one for which f of negative x equals f of x in the domain of the function. All right, well, an odd function is one for which f of negative x equals negative f of x for all x in the domain of the function. All right, so I'm going to show you an example of what that actually means. But first, for an even function, another good way to think about it is that it has a line of symmetry right on the y-axis. If it has a line of symmetry right on the y-axis, and only the, I don't say only the y-axis, but it has to have a line of symmetry on the y-axis. If it does, that means it's a even function. If it doesn't, it's not an even function. So we're going to see exactly what that f of negative x equals f of x means. So let's say we have the function f of x equals x squared. So f of x equals x squared is an even function. That even is an even function. That's this function right here. It is an even function, and I'm going to show you how that equals each other. So let's say we have some x value of 2, and we're going to see how they both equal each other. All right? So we have f of negative 2 equals f of 2. I'm taking this x and plugging it into the equation we need to prove. So f of negative 2 means that we have the function f of x at a x value of negative 2. So we're plugging this negative 2 into that x squared. So we get negative 2 squared. That should equal f of 2. So the function f of x when x equals 2 is 2 squared. Negative 2 squared is 4. 2 squared is 4. That's true. We're good to go. All right, now we're going to do the same thing with odd functions. So with odd functions, we have to prove, or we have to prove, but a function is odd when you have f of negative x equals negative f of x. That's when a function is odd. All right. And an example of an odd function, a very basic one, is f of x equals x cubed. That's this function right here. We're going to be looking at it in a few modules, in a few chapters. So that's what it is, and this is an odd function. So what that means is that for any x value, let's just say 3, f of negative x has to equal negative f of x. So we're going to use the value of x equals 3 to kind of see it. So if we have f of negative 3, that should equal negative f of 3. So that negative 3 means you have an x value of negative 3. We're plugging that negative 3 into the f of x function since our x equals negative 3. So we get negative 3 all cubed should equal a negative of that f of 3. So our x is 3. We're plugging it into the equation. We get 3 cubed. We're going to keep solving it out. Negative 3 cubed is negative 27. Right, negative 3 times negative 3 is a positive 9. Positive 9 times negative 3 is a negative 27. And then 3 cubed is just a positive 27. We have a negative on the outside still. Don't forget about it. So negative 27 equals negative 27. That's true. And that's what it means to be an odd function. That happens. And that will happen for every single x value. Right here in green, that will happen for every single x value you plug in. That will always hold true. And same thing for this one in red. No matter what x value you choose into that function, that will always happen. They will always equal each other. And that's what it means to be even or odd. So let's keep going. Now we're going to talk about stretches and compressions. All right. So, well, not stretches and compressions. We already talked about that, but we're talking about reflections now. So reflections come from the A and the B terms. We talked a little bit about that in the very first slide where we showed you guys what each parameter does, how it affects the graph. So when A is a negative number, that's a reflection over the x-axis. Over the y-axis. No, it was x-axis. Sorry. So over the x-axis, just remember A is a vertical stretch compression. That also means A is a vertical reflection. You're going to reflect vertically over the x-axis. All right. So when A equals negative 1, we're multiplying the y term, the f of x, or the y term by negative 1. So that means our transformation rule is x comma negative y, multiplying the y's by negative 1, or just changing their signs. So just go ahead and multiply each y term by a factor of negative 1, or essentially just changing the sign and flipping it over the x-axis. 0 doesn't change. 5, negative 6. All right, so let's go ahead and plot these. Negative 6, 1. Negative 3, positive 1. 1, negative 2. 2, 0 stays the same. 5, negative 6. That's what you should get. It's hard to see by the graphs, I know. But look at point to point, and you'll see that each point you just reflect it over the x-axis. From A to A, you reflected. From B to B, you reflected. Same thing with C and E's. Since D doesn't reflect, it just kind of stays where it's at. All right, so just think about it as vertical stretch. That same parameter gives you a vertical reflection, and that'll be the same thing for the next slide, where we deal with a negative B, where you have where B tells you the horizontal stretches or compressions, and also tells you the horizontal reflections or not. So you reflect horizontally over the y-axis. All right. So we're going to go ahead and do these. So B is -1. B deals directly with x. So we're multiplying the x by a factor of -1. Or in other words, changing the sign of the x term. And that's what you should get. All we did was multiply the x's by -1 or change their signs. Or the proper way to say it is you're reflecting over the y-axis. So we'll do this one. We'll go ahead and plot these. We have 6, 1 now. Right there. 3, -2. -1, 2. -2, 0. -5, +6. So go ahead and plot these, or sorry, connect the dots. Not the best looking graph. It's more or less what it should look like though. And you can see you reflected each point over the y-axis. Again, it's hard to see with just the graphs, but look at each point and you're reflecting it over the y-axis. Or in other words, if you took the graph and you fold it over this y-axis, where you're reflecting from, each point will be right on top of each other. The C with the new C with the old C, the new E with the old E, and same thing with A, B, and D. All right. So here we have some more discussion problems. So suppose a function f of x has a domain of x1, x2, in a range of y1, y2. When the graph of f of x is reflected across the x-axis, how do the domain and range change? Really for 7, 8, and 9, what I want you guys to do, pause the video, think about it for a bit, kind of try to understand all this stuff, and I'll come back and give you the answers in a bit. Okay, this is what you should have gotten. The range now changes into -y2, -y1. They change places. So you change the sign, the order from least to greatest. So the bigger one now becomes the smaller one, and the smaller one becomes the bigger one. So that's what you have to flip changes to. You can flip the which one comes first as well. For 8, it's an even function since f of -x equals f of x. That's the definition of an even function. So that makes it even. And for 9, the function that we graphed, it's neither, since neither a property of even or odd functions help for it, so it's neither. All right, and for this slide here, I want you guys to try this out yourselves. We'll go over the first one first to kind of give you an idea of what I'm looking for, and you can do the rest yourself, all right? So for g of x equals f times 3 of x, what I want you guys to do is give me the parameter first, tell me which parameter it is, a, b, h, or k, and then tell me what it equals to. So for instance, g of x equals f of 3x. Our parameter here is b, and that equals 1/3. Remember, with b's, you flip them to get your b value. And that means that we have a horizontal compression. I'm just kind of making it a little shorter, saying h comp for horizontal compression. All right, so pause the video, do the rest the same way. In a second, I will post the answers up right here. All right, so this is what you should have gotten. So pause the video, double check your work, because I think this is the last page. Oh no, it's not. We have another page to do, another slide. Sorry about that. So if you need to pause the video to copy it or compare your answers, do so now. We're going to keep going. And we're going to talk about the transformations of each of these. So g of x equals 2 times f of x minus 3 plus 4. So the very first thing we should probably always do is, what I like to do is label out my parameters, right? With a, b, h, and k. So for the first one, our a value is 2. Our b value, we don't have one, so it's just 1. Our h is a positive 3. Remember, you have to change the sign to -3 to 3, and our k is 4. So our a term tells us it's a, I guess I'm going to make it disappear. It's a vertical stretch by a factor of 2. That second one, it tells us we translate to the right by 3. And that last one, the k value of 4, tells us we go up by 4. when b is 1, it doesn't do anything. It just, you're stretching it by a factor of 1, or in other words, if you're not doing anything, it just stays the same. All right, for the second one, g of x equals negative f of x plus 2 minus 3. Same thing, just go ahead and list out your a, b, h, and k. It's really helpful so you don't get lost. You know exactly what you're looking for. Our a is negative 1. Our b is a positive 1, so it's not doing anything. Our h is negative 2. Our k is negative 3. So when our a is negative 1, that means we have a reflection over the x-axis. All right, that's when a is negative 1. When b is 1, just like before, when a or b is 1, you're multiplying by 1. That means you're not changing anything, so it's not doing anything. But our h is negative 2 means we're going left by 2. That's really small, but it's saying we're going to the left by 2. And the last one of k is negative 3 means we're going down by 3. All right, and for the last one, just like I said before, a, b, h, and k, list them out, figure out exactly which one's which. Our a is just 1, we don't have one, we have one, but it's not doing anything. Our b is a negative 1/4. Remember, whatever's here in front of the x, you flip it over. So from negative 4 to, negative 4 to negative 1/4. Our h is 1, change the sign, we have negative 1 there, it becomes a positive 1. And our k is 2. So that means when our a is 1, it doesn't do anything. But when our b is negative 1/4, that negative tells us we have, the 1/4 tells us we have a horizontal compression. And that negative tells us we have a reflection over the y-axis. That h of being 1 means we go to the right by 1. And that k of 2 tells us we go up by 2. All right? So guys, that's it for the video. Hopefully it helped. Hopefully you learned something. The next page will be just the homework. That's it. So just go ahead and do the homework. It's good practice. A lot of it really is just memorization. And memorization is going to be all about just, practicing this stuff, understanding it, filling out that chart if you have to multiple times, and just really hammering this stuff down during the homework. All that will be really helpful. And I really suggest that you do and get good at this because we're going to be dealing with graph transformations pretty much all year. All right. So anyways, video's long enough, guys. Hopefully this helped.